Ladies and gents, welcome to season 2 of the Wits Geotalks online for 2021. We've had a month or so winter break, during what is supposed to be field season, but we've had a good break, and we hope that you've missed the Geotalks. It's great to be back, and it's great to introduce you to our first speaker of season 2, who is Sara Burness. Sara, thank you for agreeing to give this Geotalk. And before Sara begins, I'll just do a very short introduction. Sara completed her undergrad and master's degree at the University of Stellenbosch, and in 2019 completed her PhD here at Wits University under the supervision of Katie Smart and Sebastian Tapper. And she's currently a research fellow, a postdoctoral research fellow at UJ, at the University of Johannesburg, in the Deep and Early Earth Processes research team. And as you'll hear in today's talk, Sara is incredibly interested in the formation and modification of Quatonic lithosphere and the petrogenesis of eclogites and rhyolithic xenoliths and diamonds. So Sara, thank you so much for agreeing to give this talk. And of course, thank you to John Hancock's and the CCIC group for sponsoring these Geotalks. And just to remind you, if you know anyone, students, fellow researchers and academics who'd like to join the mailing list, then please just send them the link that you get in the mailers, and they'll receive these talks weekly. We're also streaming on YouTube, and we have a fantastic audience on both platforms. So Sara, I'm going to hand over to you. I'll stop sharing, and we should be able to share.
Thanks, Grant. So first of all, I'm going to start off by introducing our Deep and Early Earth Processes research group. So it's quite a young group with lots of researchers in it and lots of students. So in order to do that, I'm going to quickly share a short video clip with you. Just bear for one moment while I find it. All right, here we go.
Welcome to Deep and Early Earth Processes Research. The Deep Research Group was started by Professor Sebastian Tapper at the University of Johannesburg. Sebastian's research interests include melting processes within the Earth's mantle, and particularly the formation of alkaline and carbonate-rich magmas such as kimberlites, lamperites, and carbonatites, and their roles within the geochemical cycle. The group then expanded to include Dr. Katie Smart, who is our team lead at Wits. Katie is interested in mantle-derived xenoliths and has conducted various petrologic, isotopic, and geochemical investigations on these rocks. Additionally, she has been involved in both experimental and modeling studies of volatile-bearing mafic systems, with the goal of better understanding the formation and fragmentation of the Quatonic lithospheric mantle. The research activities led by our DEEP group have been divided into various themes, and these themes include 1. The nature and origin of global kimberlite magmatism in Africa, Asia, and North America. Kimberlite pipe emplacement models, as well as macro and micro diamond relationships, including their geochemistry with implications for ancient and deep volatile cycles. 2. Alkaline and carbonatite melt generation in relatively hot Archean subduction zones, including the mineralogy of diamond-bearing lamperites. 3. Modeling the relative depths and tectonic settings of Archean continental mantle lithosphere formation, as well as the burial and unroofing histories of cratons and their mineral deposits. 4. The development of innovative geochemical tools for mineral exploration, including the petrology and isotope geochemistry of rare earth element and uranium deposits. The DEEP research team consists of a diverse group of enthusiastic researchers and students. Let's get to know them a little better. We've already introduced Katie and Sebastian. Now meet Farnes, who heads up the Geometallurgy division at UJ, a rapidly evolving field of interdisciplinary research that bridges the gap between geosciences, minerals research, metallurgy, and the mining and exploration industry. Our postdocs. Azar, whose research focus is on high-precision in-situ mineral analysis to determine the thermal and geochemical evolution of the lithospheric mantle and geochemistry of kimberlite-type rocks. Sara, who is researching in-situ gem-quality diamond formation beneath the Carpal Craton, South Africa. Our PhD students include Tendo, who is looking into the nature and origin of Paleo-Archean komatiites and related rocks from the southeastern Karpval Craton, and Ntando, who is focusing on diamondiferous lamperites in eastern Zambia. And our master's students include Steve, who's looking at the nature and origin of kimberlitic volcanism in central Angola, Roberto, whose research focus is kimberlites in Botswana, and Miranda, who is conducting geochemical and isotopic fingerprinting on gem quality diamonds. The Deep Research team has enjoyed various excursions, which have included visits to famous South African kimberlites, including the nearby Premier Kimberlite at Cullinan Mine northeast of Pretoria, which holds the record for the largest rough diamond ever to be discovered. The students also visited the Marsfontein Diamond Mine in Limpopo, the Finch Mine in the Northern Cape, as well as the world-famous Kimberley Mine, which was responsible for the diamond rush in the 1800s. Our students enjoyed the outdoor activities while learning valuable field sampling skills, which sometimes got them into trouble with local wildlife. After crushing, milling, separating, analyzing, plotting, and interpreting their data, our research team has produced numerous exciting publications in a variety of high-impact international journals, some of which include Nature Geoscience, JPET, and Chemical Geology. These journal articles can be found on the DEEP website.
So thank you everyone for bearing with me and watching that. That is just to introduce you to our group. And if you're interested in any of those projects or want to learn a little bit more, please visit our website and you can contact any of our researchers through the website. So now I'm just going to open up my talk for today. Just bear with me while I find it. All right. So thank you, everyone. Today, well, Grant's already introduced the topic of my talk, but before I start, I'd like to first thank my collaborators and my funding bodies, because without you, none of this research would have been possible. Yes. So first of all, this is the outline of my talk. So my talk is split into three main parts. I've got the first part is just an introduction to the lithospheric mantle, specifically eclogite formation within the CLM. Then we'll talk a little bit about deep volatile cycling and mantle redox, and then move on to metal transport within the CLM, as well as diamond formation. Then the second part of the talk is on Sulfurcycling on early Earth, from the Archean to the present. And then we're going to look into how you track the sulfur cycle in mantle rocks, and then go into detail on sulfur isotopes. And then finally, we're going to discuss my specific project, which is looking at disentangling the history of sulfur in CLM-derived eclogites. And in order to do this, we're looking mainly at sulfur isotope data, as well as trace element compositions of the sulfides within these eclogites. And this will give us an indication as to the different sources of sulfur in these rocks, whether the sulfur came from a primordial source or whether the sulfur has actually been recycled into the mantle from crustal sources. So let's get going with the Quatonic lithospheric mantle. So this is just an update for all of you crustal geologists, if you've forgotten about the mantle. So first, the Quatonic lithospheric mantle is in fact the uppermost portion of the Earth's mantle. So this is this little green section over here. This is a relatively cool and mechanically strong rigid layer. It's largely chemically or melt depleted, and it's welded to the base of these ancient cratons. So it floats above this kind of convecting lower mantle over here. Then the Quatonic lithospheric mantle is comprised of 99% peridotite and about 1% eclogite. And we know this from mantle-derived xenoliths and xenocrysts and diamond inclusions, which have been brought to the surface by various magmatisms, such as like kimberlites, lamperites, or lamprifiers. And peridotite looks like this at the bottom. If you look to the right-hand side, this is Harzbergite, which is a kind of depleted peridotite rock. And this is what a garnet leusolite looks, and this is kind of a more enriched garnet peridotite type rock. And then to the left here is an eclogite, which is a basaltic composition rock from the mantle. Then most researchers and most people were wondering how thick the Quatonic lithospheric mantle is. And in order to do this, we obviously can't dig a really deep hole. So researchers have analyzed these mantle xenoliths that have come up in kimberlites, and they've been able to calculate both their temperatures and their pressures using various thermometers and barometers. And these thermometers use element exchange parameters between certain minerals. So say, for example, in an eclogite, you have clinopyroxene and garnet, and you look at the iron and magnesium exchange between those two minerals, and you can calculate the temperature of where that rock last equilibrated. So once you've done that with various peridotites, you then plot them on a paleogeotherm like this over here to the right on this diagram. And then where that cuts with the mantle adiabat, that is the depth of your Quatonic lithospheric mantle. And in most cases, this is between about 180 and 250 kilometers depth. Although this is quite mathematical and theoretical, there's also physical evidence for the base of the Quatonic lithospheric mantle. So the physical evidence that we do have is in fact sheared peridotites. So peridotites from the base of the Quatonic lithospheric mantle, they become sheared because at the base there is actually, they touch the kind of more fluid asthenospheric mantle, and that shears those peridotites. So then when the kimberlites come through and pluck those peridotites into the magma and bring them to surface, you can see the result of shearing towards the base. So this is a very similar diagram. However, what I wanted to show you on this diagram is that most people think that if you get a high pressure, high temperature rock from the mantle, you might there might be the possibility to find diamonds in those rocks. But that's not always the case, because diamond actually has a very specific stability field. And you might have a rock that's come from the mantle from pretty high pressures and temperature, but it might still actually be in the graphite stability zone. So you might never find diamonds in those rocks. So now if we move on to why is the Quatonic lithospheric mantle there, and why has it remained there for such a long time? So this is this isotopic hypothesis, which really boils down to buoyancy. So you have the crust, which is relatively cold and dense and kind of sinking into the mantle. And then you have the Quatonic lithospheric mantle, which is relatively depleted, so it's relatively buoyant. So then you kind of have an equal but opposite force ratio here, which results in a relatively solid and stable package of rock, which kind of sits here floating on the asthenospheric mantle. Also, there are various different models and theories for making continental mantle. There's a plume origin. There's the oceanic lithosphere, underthrusting and imbrication, and this really only initialized at the start of the Wilson cycle at about 3 GPa, where you have subduction and imbrication of the oceanic lithosphere, and then you also have arc thickening and accretion. So all three of these are plausible, just depending on what kind of tectonic setting you're in. So now we're going to move over into eclogite formation, specifically in the CLM. So what is an eclogite rock? An eclogite rock is a high pressure, high temperature rock that comprises predominantly of garnet and clinopyroxene. So if you look on the right hand side here, it's this really beautiful rock actually with red garnet and green clinopyroxene. And there are two main theories of how this rock actually formed in the CLM. The first theory is that of kind of a magmatic origin, where scientists suggest that these eclogites are in fact high pressure melt cumulates in the mantle. So this is a kind of a basaltic type melt, which has been frozen or quenched as residues within the mantle. And then the second theory is that of subduction. So other scientists believe, or in certain cases, that some eclogites are in fact fragments of recycled oceanic crust. And there are various lines of evidence to prove that. One of those is trace elements. So in the eclogites, there's evidence for positive europium anomalies. And this is almost a ghost plagioclase signature from the protolith. So that would be kind of a gabbro, an oceanic gabbro, or I suppose basalt, that would give this signature. And then also, if you look at stable isotopes and oxygen specifically, the delta 18O composition of the mantle, or an average composition, is about 5.5 plus or minus 0.5. And if you look at quite a lot of mantle eclogites, they actually have a delta 18O composition that is either above that, quite a lot above that, or quite a lot below that. And this actually indicates interaction with low temperature seawater. So those protoliths, or the original rock, must have been at the surface of the earth. So then if we move on to evidence from radiogenic isotopes. So if you look at eclogites in general, they have enrichments in strontium, neodymium, lead, and osmium. And what's really quite interesting is that eclogitic type diamonds, so diamonds with mineral inclusions that come from kind of eclogite paragenesis, they really only came into existence at about 3 billion years ago, or about 3.5 billion years ago even. And that was at the start of the Wilson cycle, so the start of plate tectonics and subduction. And I don't think if you recycle some oceanic crust into the mantle, and that's the start of E-type diamond formation, then there's a lot of truth behind the recycled origin for eclogites and potentially eclogite type diamond formation. Also, eclogite type diamonds not only formed at about 3 GA, they also have younger ages at about 2 and even 1 GA. And these overlap with known subduction events around the world, and specifically on the Carpal craton as well. And these kind of overlap with craton suturing, as well as younger mobile belt activity. So now if we take a look at the deep volatile cycling. So the important volatiles in the mantle are really kind of carbon, oxygen, hydrogen, which is water, and sulfur. And it's important to note that even the smallest quantities of these volatiles in the mantle actually affect the properties of mantle rocks as well as melts and fluids. And what I really want you to take away from the slide is that this kind of deep carbon cycle over here, without these elements, the world, or the earth, would be a very different place to what we know it would be really static and stagnant, and life as we know it would not exist. So now if we kind of focus a little bit on the redox of the Quatonic lithospheric mantle through time. So redox is really the oxygenation state of the mantle. So if you look at this diagram on the right hand side here, this log FO2 is obviously redox, and here against pressure, so going down with depth. And as you can see here with various eclogites and peridotite nodules, firstly, there are various proxies that you can use to calculate mantle redox. In this case, we've used the iron 3+ content in garnet. And you can see by calculating the redox that actually the deeper you go in the mantle, the more reducing the CLM becomes. And this is really important for certain volatiles as well, and specifically sulfur, because they are also dependent, or their speciation is dependent on the redox composition of the mantle. So if this is your FMQ buffer at 0, going down -1, 2, 3, etc., everything below the FMQ buffer, sulfur the sulfide species is actually dominant. And everything above the FMQ buffer over here, the sulfur species is actually sulfate dominant. So if you look at these mantle rocks over here, the predominant sulfur species in these rocks would be a sulfide. So that's why you find predominantly sulfide minerals within mantle rocks, unless obviously they are metasomatized by a carbonatite or an oxidizing fluid, and then potentially you'll find a sulfate species or a sulfate mineral within these rocks. So now, just as in a little aside, sulfur is really, really important for geology and mineral deposits, and is actually one of the most important volatiles in the deep volatile cycling. So sulfide minerals are really important because they control both the PGE and chalcophile element budget of the CLM. And obviously their behavior during melting controls the movement of these economically important metals in and around the CLM, and obviously onto the surface. So melt generation is obviously affected by the percentage of volatiles that are there, and low degree CO2 fueled melting will produce a kimberlite. And kimberlites, because they're quite CO2 rich, they actually do not have a lot of sulfur in them, and they kind of pluck off some diamonds and bring the diamonds to the surface, and that's the main kind of deposit type. Whereas a high degree melting will produce kind of a large volume melt, and this melt will interact with kind of crustal rocks, and you might produce porphyry copper, or even a lower degree melting copper rich deposits in the crust. And what's really important to note with all of this is that sulfur is the main driving factor for these deposit types, and these really economically important deposit types. Then if we look at diamond formation within the Quatonic lithospheric mantle, so diamonds are a really good commodity, and diamonds are a girl's best friend. So it's really important for scientists to understand how diamonds have formed in order to, help with exploration and the diamond industry. So people have looked at diamonds for many years now, and they found that fibrous diamonds, the ones on the bottom left here, they actually include some of the fluid that actually form the diamond. And by being able to characterize these fluids, scientists have been able to come up or to better understand the type of fluid that forms diamonds. And by doing this, scientists have realized that diamonds actually form from various types of fluids that may have both carbon, hydrogen, and sulfur volatiles in the fluid. Then also in eclogites specifically, if you look at metasomatized eclogites that are diamond bearing, often the diamonds follow vein lines, and so it looks like the diamonds have actually grown from the metasomatic fluid that has metasomatized these eclogites, and that's also important to note. And then finally, if you look on the right hand side here, this is a sulfur or sulfide inclusion within a diamond, and diamonds often have various inclusions with them, including various silicate minerals. But mineral inclusions in diamonds are actually dominated by sulfides to such an extent that they're actually considered a different petrogenetic group. And this is important because sulfur then may actually be a catalyst for diamond growth. So if you have a oxidizing kind of carbon-bearing fluid or carbonate-bearing fluid that's kind of traversing through the CLM, and it comes into contact with a reduced sulfide, it's likely that the sulfur will reduce the carbon to a point where it might actually form diamond. So yes, that was the end of my bombardment of the Quatonic lithospheric mantle, but then hopefully everyone's on the same page with how important sulfur actually is within the Quatonic lithospheric mantle, and that it actually results in a lot of different, diamond forming events as well as metal transport. So now if we move on to sulfurcycling on the early Earth, which is kind of from the Archean to present, what we're really going to focus on is actually sulfur isotopes and how they help us track the sulfur cycle. But before we start, there are kind of two main definitions that everyone kind of should know about sulfur isotopes. So the abundance of sulfur isotopes on Earth is actually mass dependent, and it has been shaped by various surface, lithosphere, and mantle processes for billions of years. Then sulfur is able to be mass independently fractionated, and what this means is actually that this sulfur is characterized by the excess or deficit of 33S, and this can also be expressed as S-MIF. So then if we move on to the sulfur cycle on early Earth, so this is kind of in the Mesoarchean. So in the Mesoarchean, you had a lot of UV radiation that came into the atmosphere, and this bombarded sulfur and produced both oxidized and reduced sulfur species with both positive and negative S-MIF signatures. And similar photolytic reactions were going on in sediments on the surface of the Earth. However, this is both in stark contrast to what was happening in the mantle. So in the mantle, high temperature partial melting reactions actually can't mass independently fractionate sulfur. So this S-MIF signature could never be produced in the mantle itself because high temperature melting just can't do that. So then you had the initiation of plate tectonics, and this introduced some of this S-MIF signature into the mantle. And we know this from various diamond inclusions or sulfide diamond inclusions that exhibit an S-MIF signature. And then also there are some mantle-derived magmas such as OIBs that also have evidence of an S-MIF signature. So then if we move on to kind of a more modern sulfur cycle, but before this modern time, you actually had the Proterozoic where you had the great oxygenation event. And this put a huge amount of oxygen into the atmosphere and created what we call today the modern atmosphere and ozone layer. And this actually reduced the amount of UV radiation that was able to come into the atmosphere. And as a consequence, it actually, the S-MIF signature, this S-MIF signature disappeared from the rock record. And this is really important because it puts constraints on the age of the sulfur that's been recycled into the mantle. So ancient sulfur from the Archean will present an S-MIF signature, or most of the time if it came from crustal sediments, whereas more modern sulfur that's been recycled won't have that S-MIF signature. Also, with a lot of oxygen kind of in the atmosphere and on the surface of the Earth, delta 34S was able to be fractionated to a greater extent, so to about -72 per mole to +20 per mole in sediments on the ocean floor, whereas in the Archean, the delta 34S compositions were only fractionated to within 10 units, I suppose, of 0. Then you also have oceanic sulfate in the oceans, and these little sulfates could be reduced to sulfides by microorganisms, and they also might impart a small S-MIF signature onto these sulfides, but this signature is actually not as great as the S-MIF signature that would be produced through photolytic reactions. So that was just really an update and an overall introduction to the sulfur cycle. And if we move on to this next slide over here, and we look at this diagram by Walters et al. 2019, you can see that in an oceanic kind of subducting setting, that you have various sources of sulfur. So you've got sulfides in your oceanic crust, you've got sulfides and sulfates in your oceanic sediments, you've got sediments that might have come off cratons and into the ocean, you've also got sulfates from the seawater. So there's a large amount of different sources that your sulfur might have come from and then been subducted into the mantle. Also, for a long time, lots of researchers thought that because sulfur is quite volatile, that during subduction it would have been extracted from all of these sources into melts and then it kind of disappeared into into different other magma forming kind of events. So now what we are trying to do with our sulfides in our CLM derived eclogites, we want to see if our sulfides are actually primordial, so whether our sulfides have come from a mantle source, or whether we can prove that our sulfides have come from one of these sources here on the surface of the Earth and have actually been retained in our eclogites to mantle depths. So if we move on to the slide over here, so our eclogite xenoliths we actually obtained from 3 different kimberlites on the Karpal Craton, and these kimberlites include Premier, which is located on the eastern limb of the Bushveld complex, kind of central-ish Karpal Craton. Then also we got eclogites from Roberts Victor and from Jacobsfontein, which are towards the southern margin of the craton. Also, the kimberlites are of various Mesozoic to Proterozoic ages, so they also have a distinct age range of our kind of kimberlites. So when we looked at our eclogites initially, we could prove that they were fragments of subducted oceanic crust. So if we look back and we looked at their chemistries, our eclogites showed evidence of europium anomalies. They also had oxygen isotope compositions, if you look at this diagram over here, that are well above the mantle range of 5.5 plus or minus 0.5. So we could prove quite quite carefully that these eclogites are in fact fragments of subducted oceanic crust. What we don't know a lot about, however, is the multiple sulfur isotope composition of mantle rocks and magmas, and specifically mantle eclogites. From the few data that does exist, we can see that the eclogite zenoliths actually have a wide range in delta 34S compositions, from about -13 to about +20 per mole. And also, if we look at the eclogite paragenesis sulfide included diamonds, they have a similar delta 34S range, but they also have a cap 33S or S myth of -0.5 to +1.65. And this is actually evidence that there must have been recycling on the Carpal craton since at least the Archean, because this is evidence of sulfur that's been around since ancient times. So now if we move on to, these are just some fun facts about the kimberlites that our samples came from. So Premier, or the Premier kimberlite that hosts the Cullinan mine, is actually a really important kimberlite. So this kimberlite is actually the largest kimberlite in the whole of South Africa. It's 32 hectares in size, and it's the largest pipe of 11 pipes in its cluster. It's also really famous because the Cullinan diamond was found there, and this is actually the largest rough diamond that's ever been found at about 3,100 carats. The mine is also really famous because it also hosts a number of large type 2B blue stones, which is similar to the stone on the right-hand side here. And it's blue because of some boron impurities in it. And lots of these blue stones are actually sitting in the crown jewels. And then also what's quite cool about this mine is that they actually offer mine tours. And that's really cool because everyone who's interested in the diamond process and diamond mining can go and have a tour of the actual complex at top, but you can also go underground and see how diamonds are excavated and out of the ground. So that's really quite cool. And then this is just some important information on the Roberts Victor kimberlite and the eclogites that we're looking at from there. So the Roberts Victor kimberlite is unique in the fact that it has a xenolith cargo that's pretty dominated by eclogite. And that's quite incredible because we know that eclogite is actually only about 1% of the Quatonic lithospheric mantle. So for this one kimberlite to pick up 25% of its xenolith cargo as eclogite is actually quite incredible. So now we're just kind of moving back to our samples. So first of all, I'm going to introduce our eclogites and what we found out about them, and then move on to the sulfides that they host. So first of all, this is kind of our eclogite petrogenetic model. So we found two main groups of eclogites. The first group last equilibrated close to the base of the Quatonic lithospheric mantle. And these eclogites are in fact melt depleted. So they have light earth element depleted REE patterns or trace element patterns. And then our second group that last equilibrated close to mid-lithospheric levels, they are light earth element enriched. So then if we move over to the right-hand side diagram, we were able to calculate the redox compositions of our eclogites using the iron 3+ content of our garnets. And as you can see from this diagram over here, when we plotted our eclogites, the majority are actually pretty reducing, except for a couple of the deepest eclogites or deepest derived eclogites, which actually smear to a little bit more kind of oxidizing compositions. And this is interesting because they might have interacted with a kind of carbonate rich fluid or melt, which changed the redox composition to kind of more oxidizing compositions. So then we looked into the sulfides within these eclogites, and we saw that they actually also had two distinct groups. So the eclogites from the base of the Quatonic lithospheric mantle, so these are the deepest eclogites that were pretty melt depleted. Their sulfides actually have PGE affinities for sulfides that are left behind after partial melting. And in some cases, the sulfides also had affinities to kimberlite type melts. Then in contrast, sulfides from mid-lithospheric eclogites. So these are the ones that equilibrated at shallower PTs, and they actually had PGE affinities similar to broadly basaltic magmas. So they were kind of more enriched in PGE. So now that we have two different sets of eclogites and two different sets of sulfides, or chemically distinct different sulfides, we wanted to see if these two sets of sulfides actually came from two different sources. And in order to do this, we wanted to look at their sulfur isotopes. So we took the eclogites to the University of Pretoria, where we used the Sulfrag to split up the eclogites and separate the sulfides. And once we'd separated the sulfides and we found 19 of the kind of least fireable, best-looking grains, we then took those grains to the LG Sims in Nancy in France, and we analyzed them for their multiple sulfur isotopes. So over here on the right-hand side, these are just some examples of our sulfides with various compositions throughout, and these are just our analytical spots from the Sims. All right, so this is in general the data we got from our sulfides. So first of all, the majority of our sulfur isotope compositions plot between these two lines. And these two kind of lines or arrays depict mass-dependent sulfur isotope fractionation. So this doesn't mean that the sulfur wasn't recycled. It just means that the sulfur might not have been particularly ancient. Although we did find one small S-Smith anomaly of around -0.29 at Jagersfontein, and this might indicate some ancient sulfur was in the system. However, we've still plotted our sulfides according to their chemistries. So the low PGE sulfides have delta 34S compositions from about -5 to +2.5. Those are those blue crosses over there. And then we have the high PGE sulfides from the mid-lithospheric eclogites, and they have delta 34S compositions from about -3.9 to +3.44. So although these two groups overlap, the high PGE sulfides actually tend to congregate at more positive values over here. Then we had one completely different outlier, which was some sulfide from sample MBK from Roberts Victor. And this eclogite actually had sulfides that exhibited delta 34S compositions from +13 all the way up to +29. And this +29 is really quite extraordinary because it's actually the most in delta 34 enriched value that's ever been found for mantle derived rocks. So it used to be about +8 or +13, where the mantle rocks the highest delta 34S for mantle rocks, and now it's been extended all the way to +29. Also, what's important to note is that S-MIF, which is cap 33S, is obviously generated by photolytic reactions, but you can also have a small cap 33S produced through the fractionation of, or the mass-dependent fractionation of 34S. So the more you fractionate 34S, you might get a little peak in cap 33S. But as you can see here for these samples, that they actually don't follow any kind of correlation. So the more delta 34S fractionation you get, it doesn't correspond to more cap 33S. So now we're going to move on to trying to integrate our sulfur isotope data with our eclogite model. So I know there's a lot of writing on this slide, but if you just focus on the diagram on the left-hand side here, we're trying to say that the eclogite depth of origin and redox state actually correlates quite well with the sulfide PGE composition as well as sulfur isotopic signature. So for example, our deepest derived eclogites have higher FO2 or redox compositions. They also light rare earth element depleted and melt depleted. They have low PGE sulfides, and they also have a negative mantle-like mean delta 34S value of around -2 per mol. Then our second set of eclogites, which are this shallower group over here, They have lower FO2 values, so they kind of are more reducing. They are enriched in light rare earth elements. They have sulfides with higher PGE contents, and then they also have a positive mean delta 34S value of about positive 1.3. Then, if you look at our outlier, MBK, MBK is really quite oxidized, the eclogite. And it's enriched in light rare earth elements in a similar way to the shallower eclogite group over here. But their sulfides are quite distinct in the fact that they are quite palladium enriched. They're quite different to our high PGE sulfides here and our low PGE sulfides there. They also have the highest mean positive delta 34S value of about 21.9 per mol, which plots quite far away from these other two groups that sit over here. So then what does this mean for really interpreting this data? How does this fit into the greater scheme of subduction, or where the sulfurs come from? So we have plotted our sulfides on these two main diagrams over here. So if you focus on the left-hand diagram, we've plotted PGE indices against each other. And you can see that our depleted sulfides, they actually overlap with residual sulfides from both ARC and CLM peridiotites. So these are sulfides that have been left behind after partial melting. And that would be expected because these eclogites are actually melt depleted and have obviously gone through rigorous kind of subduction melting processes, metamorphic processes, and all the way into the deep mantle. Then our red crosses, they overlap to some extent with metasomatic sulfide from both ARC and CLM peridiotites. But what's also important to note is that they also overlap with sulfide diamond inclusions from E-type diamonds from the Karpal craton. And these diamonds have actually been inferred to have formed from Paleoproterozoic subduction zone fluids. So these fluids are thought to come from a subduction source, so potentially the sulfur has also come from the crust. Then you look at MBK, which is kind of an outlier and away from everything else that we've found on this graph. So we've kept our PGE indice on this right-hand side here, and we've plotted it against the delta 34S composition of our sulfides. And as you can see, over here, that the majority of sulfides actually overlap with altered oceanic crustal sulfur. And this is quite important because then we interpret that our sulfurs actually come from the altered oceanic crustal protolith and is being subducted all the way down into mid-lithospheric to deep lithospheric P's and T's. Then if you look at MBK, which was our outlier over here, this MBK actually overlaps with seawater sulfate, its delta 34S composition. And this is quite interesting because seawater sulfate is probably a really small proportion of the oceanic slab that is subducted into the mantle. However, it is seen to survive all the way down to at least 4 GPa and 1,000 degrees Celsius, which is quite interesting because I think a lot of researchers suggest that sulfur is quite volatile and must leave the oceanic slab before it gets to such great depths. So all of this research is soon to be published this week, actually, in Burness et al. EPSL. So if you're interested in reading up more about this, please go and have a squiz at our paper. And yes, I'm open to any questions. Thank you.
Sarah, thank you very much. That was fascinating, very comprehensive, and incredibly interesting. So thank you very much. And I'm sure we have time, and I'm sure we have many questions. So keep your slides at hand, Sarah, just in case you need to go back to them.
Share.
Yeah, you can just share. So just to remind the audience, for those of you that haven't attended the Geotalk for several months, there are 2 ways that you can ask questions. You can either raise your hand, which you'll find in the bottom bar. If you just hover over the bottom of your screen, raise your hand and we'll unmute you. And you can ask a question verbally, or you can simply type a question into the Q&A box and we'll read it out and Sarah will answer it. So do we have any questions at that point? give it a second or two because there's normally a bit of a lag. But I have a question. Maybe I'll start with a question, Sarah, just to warm everybody up. If you go back to your interpretation slide, one thing that really fascinates me, and you mentioned it briefly, that those red crosses, I think I heard this correctly, overlap with diamond inclusion compositions, if I'm correct. What fascinates me is that diamond inclusions in the carpel, or beneath the carpel, have really significant, in some cases, mass-independent fractionation and cap-33 sulfur. So I'm just wondering why the disconnect between diamond inclusions, sulfide diamond inclusions, and sulfides and eclogites, even though they overlap in a PGE kind of sense.
Yeah, absolutely. So our sulfide inclusions in diamonds, so often there is that S-MIF signature, and that's kind of been implicated with, sulfur-bearing sediments on the surface of the Earth. So those would obviously have been in interaction with the atmosphere and these photolytic reactions. But there are also diamond sulfide inclusions that are really old, that don't have those S-MIF signatures, like we see in these specific eclogites. And that's potentially because the sulfur that was included into those diamonds came from, say, an oceanic crust or a source that was never exposed to light. So it would never have got that S-MIF signature, even though it might be quite ancient sulfur. That's kind of just one explanation for it.
Okay, so effectively there could be different sources for diamond inclusions versus eclogites, different sources.
Absolutely, and not all diamond included sulfides have that S-MIF signature, even really ancient sulfide inclusions.
Okay, cool.
Cool.
All right, are there any questions? I don't see any raised hands. It looks like it's very comprehensive, Sarah. You haven't listed any questions. You can raise your hand at the bottom and I'll allow you to speak, or simply type a question into the Q&A.
I see one here. It says, the very positive delta 34S signals in MBK are quite interesting. What process can lead to the genesis of those high delta 34S signals? Why seawater sulfate, that positive? Okay, so I think the question is why. So seawater sulfate is positive 21 per mol, and ours is all the way to kind of positive 28 per mol. So that might be some interaction. So interaction with seawater is our best explanation for now. So there hasn't really been any evidence for higher than that fractionation. So yeah, if you have any suggestions, let me know. I don't have a better explanation than that it came from the seawater source, but you also have peridotites in the oceanic lithosphere, serpentinites, that have been fractionated to positive, say, 30 per mol, delta 34S, and those have been found in subduction zone, kind of slivers of subduction zone rocks. So that potentially might also have been a source for the 34S. So yeah, something like that.
Okay, fantastic. Thank you, Sarah. We have a question from George Henry. George, I'm going to allow you to talk and you can unmute yourself.
Thank you, Grant. Thank you, Sarah, for the fantastic talk. Sarah, I'm just curious to know whether you have dated the diamonds that you were working on, because you have different ages of kimberlites, and just curious about that. Thank you.
Cool. So for this specific study, we didn't actually look at the inclusions in diamonds specifically, but I know there are various ways to do it. So rhenium, osmium ages, lots of people have looked at that. So the future work for this study, we're going to be looking, potentially, hopefully, we're going to be looking at the sulfide inclusions in specific diamonds from the carpel, and then we'll be able to date the sulfide as well as get the sulfur isotope composition, and then that would be quite nice so that you can overlap both data. So you've got an age data and you've got the sulfur isotope, and you can see how old it is and where it's come from.
Thank you.
Thank you for joining us, George. Are there any other questions? One last question or opportunity to raise your hand or post in the chat or the Q&A. All right, I don't see any messages popping up. So thank you for those questions. And thank you, Sarah, for a really fantastic talk. And we look forward to reading the EPSL paper when it comes out.
Thank you.
And hopefully, Sarah, if you have a few minutes after this, we always like to have a little bit of networking, virtual networking after the talk. So if anyone is interested in asking some more casual questions of Sarah, or just simply chatting because you've been at your desk alone all day, then simply raise your hand and we'll promote you to a panelist and we can have some interactive virtual networking. But before we do that, let me just share my screen with you to inform you of next week's talk. So you should all be able to see my screen now. Next week's talk is by Zuyang Meng from the University of Michigan. He's a postdoc there, and he'll be talking about magmatic controls on formation of some representative Archean Paleoproterozoic porphyry type copper plus gold deposits. And Zuyang has been to South Africa before and has spent a lot of time working on the Hybe porphyry copper deposit, which is one of the few Proterozoic porphyry copper deposits. So hopefully you can join us for that talk. And then I also just want to remind you of a fundraising drive that we're currently running in honor of Matt Kitching. As many of you know, Matt Kitching passed away recently, and he would have touched every graduate and every staff member's life in the School of Geosciences. And he dedicated a lot of time to the museum. And so in his honor, we would like to renovate the museum and make it into a wonderful public space for everyone. And so if you're interested in contributing to this fundraising effort in honor of Matt, then just raise your camera up to that QR code and you can scan it and it will take you to a donation page, and that we'd be most appreciative of that. If you are keen on doing that, you just have to select other under the project option and put the reference Matt Museum Geos. And we'll dedicate that money to renovating the museum in Matt's honor. So thank you for that. And thank you once again, Sarah, much appreciated. And we look forward to seeing everyone next week.